Hi Year 12s, it's Mr. Lim here again, and this is the third video on half equations. Hopefully we'll go through this one a bit quicker. Okay, so we're going to be learning about half equations. You're going to have to be able to write half equations from text or balanced equations, and then you're going to be able to combine them. Okay, so half equations, what are they? Each redox reaction is made up of a reduction and an oxidation. We learned that in the first video. We can show each of these individually as half equations, which show the reactants and products of each part, that's the oxidation and reduction, and how many electrons are lost and gained. It's useful to show these as half equations because then you can interchange oxidation reactions with other reduction reactions. So say you have oxidation number one, or oxidation equation number one, you can interchange that with any of the reduction equations and just say what it would look like and what products would be made. Okay, so half equations, you're going to have to copy all this down. I'm not going to read through it now because I have a couple of examples, so you can pause the video and copy it down, and then go through the example with me. Okay, so first one, first example we have is copper. Okay, so Cu turning into Cu2+. Okay, so this is a half equation. It's not done yet because we haven't done all the steps, so let's go through. Identified the reactants and products. We've identified them as Cu and Cu2+. All right, balance all non-oxygen and non-hydrogen atoms. So copper is a non-hydrogen and non-oxygen atom, so therefore we have to try and balance them. So if there's one on each side, that's balanced, done. Sometimes there'll be an imbalance of oxygen atoms, not here. Sometimes there'll be an imbalance of hydrogen atoms, not here. Okay, so let's do step 5. Calculate the overall charge on each side of the equation. Okay, so the overall charge here is 0 for the left-hand side and positive 2 on the right-hand side. Okay, taking into account the coefficients of any substance as well. If there were any coefficients, we'd have to take them into account. Then work out which side is more positive. That's the right-hand side for this one. And to that side, add electrons to reduce the charge of that side to equal the other side. So we need to add some electrons to reduce the overall charge of this side, the product side, to equal the reactant side, right? And how many electrons should we add? We should add 2 electrons because that would make a total of -2, and therefore this total would be 0, and that total would be 0 as well, and therefore we would have a balanced charged. Okay, let's try the next one. Okay, so let's try hydrogen peroxide. So this is one of those special ones that oxygen will change into something else. Okay, it has a different oxidation number in the peroxide form. Okay, so let's go through this. Identify the products and reactants. Did that. Balance all non-oxygen and non-hydrogen atoms. None there. Step 3. There will be an imbalance of oxygen atoms in the equation. Okay, yes there is. So we need to add waters to the side that is deficient in oxygens. Okay, so we're going to add waters. To which side? The right-hand side, because it's only got 1 oxygen. So we're going to add a water, so we're just going to add a 2 there, because that's a water already. Alright, now there is an imbalance in hydrogen atoms. There are 4 hydrogens on the right-hand side, and only 2 hydrogens on the left-hand side. So we're going to add hydrogen ions to the side that is deficient in hydrogen atoms, which has less, which is the left-hand side. So we're going to add 2 hydrogen ions onto the left-hand side. Okay, then calculate the overall charge on each side. The overall charge on this side is, well, that's +2 and that's 0, so that's total charge of +2. That's a charge of 0, so that's a charge of 0. So which side is more positive? The left-hand side, the reactants. To that side, add electrons to balance out and reduce the charge so that they're equal. Okay, so how many electrons do I need to add? 2 electrons over to this side here. Okay, that will be a -2, and that will make the overall charge of that one 0. Okay, that's that example. And the last example, let's get rid of all of this. The last example, the dichromate ion, which we dealt with before in oxidation number, turning into chromium ion. Okay, so let's go through this. We have to first of all balance out the non-oxygen, non-hydrogen atoms. Okay, so we have to balance out those. There are 2 chromiums on the left-hand side. There is 1 chromium on the right-hand side, so we're going to balance that out by adding a 2 there. Now we're going to balance the oxygen atoms. We need to add 7 waters to the right-hand side because you've got 7 oxygens on the left-hand side. Now we've got a whole bunch of hydrogens we need to add. How many hydrogens do we need to add on to the left-hand side? 14. 14 hydrogens added to the left-hand side. So now we need to balance out the charges. So let's have a look at the charges. We've got plus 14 here. Oops, not plus 114, plus 14. And a negative 2 here, so that's a total of positive 12. Happy with that? We've got a total charge here of positive 6 and 0, so a total charge of positive 6. Which side is more positive? It's the left-hand side. So therefore, we need to add electrons to the left-hand side. How many electrons? 6. 6e minus to make that negative 6 to make that total positive 6 only. So now this one and that one match. Okay, so that's making a half equation just from the reactants and the products. It's going to be an important skill for you to work out. Once you have your two half equations, you can combine them into a single full redox reactions. Okay, so you can go copy all this down in a moment, but the idea is that you want to have the same number of electrons being lost as the same number as being gained. Okay, so let's go through an example. Here on the left hand side, this half equation is gaining 2 electrons. Okay, and on the right hand side, this equation is only losing 1 electron. So we need to make sure that those two equations are balanced in their number of electrons lost and gained when we combine them together. So we need to, first of all, determine the lowest common multiple of the coefficients of the number of electrons in both equations. So what's the coefficient here? 2. What's the coefficient here? 1. All right. So those two coefficients, 2 and 1, what's the lowest common multiple? The lowest common multiple of those two is 2. Right? Then you need to multiply both equations by the number needed to bring the coefficient of the number of electrons to the lowest common multiple, so that both equations are losing and gaining the same number of electrons. Okay, so the lowest common multiple is 2, so what you have to multiply this one by? Well, you multiply it by 1, and this one you have to multiply it by 2, because that's a 1 coefficient there. Okay, so you have to multiply this one, the left-hand side 1 by 1, the right-hand side 1 by 2. All right. Then you write all of the reactants and products together in one equation, ensuring you transfer all coefficients. So this left-hand side equation, we're going to write out all the reactants here, timesing it by 1. So H2O2 times by 1 is just one of them. The hydrogens, 2 of them, timesing by 1. And those are all and the electrons, the 2 electrons here. Okay. Then we have to add in all of the reactants from the second half equation. So that happens to be 2 of the silvers. Okay? So that's just this thing here, times it by 2. Okay? So then we have to do all of the products. Okay? So all of the products. So 2 waters. Oh, no, that's not supposed to be a plus. That's supposed to be an arrow. We have 2 waters as the products on that side, timesing it by 1, plus 2 times this one here, 2 times the silver ions, plus 2 times the electrons. Then, step 4, cancel out any substances that appear on both sides of the equations, only cancel out the appropriate number of coefficients of that substance, so the equation still balances. Okay, so what here is on both sides, and they're exactly the same? The electrons. Okay, so the electrons can be cancelled. The electrons are always cancelled. So technically you don't really need to write out the electrons when you're doing it. And that's the only thing that is cancelled for this 2 half equations. Let's go practice some more. Okay, let's write out this half equation. So periodic acid was discovered, blah, 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 blah. Orthoperiodic acid, that's this one here. And metaperiodic acid, they're 2 different forms, right? Orthoperiodic acid is a weak acid, blah, 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 blah. And it's shown in that diagram there. So that's the orthoperiodic acid molecule, and that's that thing there. All right. Orthoperiodic acid is an oxidizing agent and an oxidant of moderate strength that can be produced by the electrochemical oxidation of iodic acid. So that's this brand new substance here, using a lead 2 oxide anode, and you don't have to worry about that at the moment. All right. Write the half equation for production of orthoperiodic acid, that's the green thing, from iodic acid, which is the purple thing, so we're not dealing with the blue thing yet, assuming acidic conditions. Okay, so let's go through that. So let's write out our half equation. Okay, so we're starting, okay, first of all, what's the reactant here? It's the iodic acid, okay, because it says from iodic acid. So HiO3, that's our reactant. Okay, notice how I give myself a bit of space here, so I'm going to write out some other electrons and stuff like that. Okay, and it's making orthoperiodic acid, which is the HiO6. Okay, so first of all, what are we going to do? Balance out the non-oxygen, non-hydrogen elements. That's the I, they're balanced already. Now we're going to add some waters to balance out the oxygens. On the product side, you got 6. On the reactant side, you got 3. So you're going to add 3 waters here. Okay, now we're going to balance out the hydrogens. So I have 1, 2, 3, 4, 5, 6 on 7 hydrogens on the reactant side. And I have 5 hydrogens on the product side. So the products need a few more hydrogens. How many? 2 more. Okay, and therefore that's done. Now I can balance out the charges. So overall the charges here are, well, 0, 0, 0, and positive 2. Okay, which side is more positive? The positive 2 side, which means that I need to add 2 electrons to this side to make it even. Okay, and that is your half equation for this particular question. Let's move on. Write the balanced half equation for, okay, so this piece of information here is new. When metaperiodic acid, that's this blue one here, metaperiodic acid is heated further, the compound diiodine pentaoxide, which is a brand new thing that we're dealing with, is formed. Diiodine pentaoxide is water soluble, blah, 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 blah. Write the balanced half equation for the formulation of diiodine pentaoxide from metaperiodic acid, assuming acidic conditions. Okay, include phase symbols, and we'll just, we'll go through that carefully here. All right. So let's have a look here. So what are our 2 substances? What's our reactant? It's the metaperiodic acid, the HiO4. Okay, and that's forming the diiodine pentaoxide. Okay. It's assuming acidic conditions, so it means it has to be water soluble. So water soluble, so this is aqueous. It's an acid, so therefore that also must be soluble. Okay, so they're both aqueuses. Okay, so let's move on. Let's first of all balance out the non-oxygen and hydrogen elements. So that's the iodine. Now there are 2 on the right-hand side, and there's only 1 on the left-hand side, so I got to balance that out by having a 2 there. Now I'm going to balance out the oxygens. So the oxygens, there are 4 on the left-hand side. Sorry, there are 8 on the left-hand side because I got a coefficient of 2 there. 8 on the left, 5 on the right. If I have only 8 on the, if I have 8 on the left, 5 on the right, I need to add 3 waters to balance out the oxygens. Okay. Now I've got too many hydrogens. Okay, so I've got 6 hydrogens on the right, and 2 hydrogens on the left, so I need to add a few hydrogens here, 4 of them in fact. Okay, and then I can have a look at the charges. So that's 0, that's positive 4, that's 0, that's 0. So therefore I need to, which side is more positive? That's the left hand side. I need to add 4 electrons to this thing. Okay, don't forget the state symbols, that one there and that one there. Okay. And that one's this question here. Let's do another one. Okay. When tin metal is placed in an acidified solution containing a weak hydrogen chromate, a deep green solution containing chromium ions is formed, and the tin metal dissolves, producing tin ions. Okay, so let's have a look at what you've got here. You've got information. You've got tin metal, first thing, weak acid hydrogen chromate, which is that thing there, right? You've got chromium ions, and you've got tin 2 ions. Okay, you've got 4 things. 2 of them are going to be part of the one half equation, and 2 of them are going to be part of another half equation. So the tin metal and the tin ions are going to be in one half equation because, there's tin both in those. All right, so let's go through it. tin, Sn, goes to tin, two ions. Sn2 plus. Okay, let's look at their oxidation numbers. Oxidation number of tin metal, 0 because it's in its elemental state. Tin plus 2 because it's a monoatomic ion. Did that number go up or down? That number went up, so therefore it is oxidation. So tin is our oxidation equation. Okay, so let's go through vote. Sn goes to Sn2 plus. Okay. No oxygens, no hydrogens, all the tin atoms are balanced. We just need to add some electrons, and we're adding electrons to here. Okay, now let's go to the hydrogen chromate. So it's starting out as hydrogen chromate, and it's turning into chromium 3 plus ions. Okay, so balance out the chromiums, they're balanced. Balance out the oxygens by adding some waters here. Balance out the hydrogens by adding some hydrogens here. And then balancing out the electrons of the charges, you've got a total of positive 6 on the left-hand side, positive 6 on the left-hand side, and a positive 3 on the right-hand side, which means that the left-hand side is more positive, so I need to add in a couple of electrons, 3 of them in fact, on that side there. All right, and you should also add in your state symbols, but I'm not going to do that now. All right, overall redox reaction. Okay, so remember, we've got to make sure that the number of electrons lost and gained are equal. So this one here, okay, wait, first of all, we've got to work out the lowest common multiple of the coefficients of the electrons. Lowest common multiple of 2 and 3 is 6. Okay, so we need to multiply this one out by 3 to get to 6, and this one out by 2 to get to 6. So let's write that all out. 3Sn plus 14H plus 2HCrO4 minus goes to 3Sn2 plus 2Cr3 plus 8H2O. Okay, and that is your balanced equation. Right, last slide. Ooh, multiple choice. Methanol air battery is a special fuel cell that involves methanol reacting directly with oxygen from air. The relevant half equations are shown below. Okay, look at both of these half equations. The electrons are both on the left-hand side of the arrows, which means that they're both gaining electrons, which means that they're both reducing. Now, you can't have both of them reducing because you have to have one as an oxidation and one as a reduction. So you read the question carefully, and it says methanol reacting with oxygen. So here's your oxygen. Here is your methanol, and you'll learn the formula of methanol later on, but that's the methanol. Okay, so what it is that this reaction is going backwards, and that reaction is going forward, and the upper one is going forward. Okay, so we need to write out the balanced overall equation. So we need to work out, first of all, the lowest common multiple of 4 and 6, which happens to be 12, not 24. You don't just multiply them out. So therefore, the lowest common multiple, to get this one to the lowest common multiple, you times this one by 3, and you times this one by 2. Okay, now remember that the bottom one is going backwards. So if we were to write out this thing here, we have to write out all the reactants first. So 3O2 plus 6H2O plus all of the reactants, that's these things here. So 2CH3OH plus 2H2O, which means that we can probably turn that to 8H2O, but that's fine. That goes to all of the products, 3OH, no wait, no, not 3, 12OH minus plus 2CO2 plus 12H plus. Okay, now, a couple of things. That OH minus and that H plus can probably combine, and so therefore we can just write 12H2O. Okay, Also that, that H2O here, the two of them there, can combine with those ones to make 8 H2O. Then we've also got to cancel out the waters. So there are 8 on the left-hand side here, and there are 12 on the right-hand side over here. And so therefore, we're going to cancel out all of these 8 with 4 and leave 4 of these left over. And which one's that one? That one's D. Okay, that's it. Ask any questions you have in class. That's it.